All right, yeah, please, Mario, whenever you're ready.
Okay, so let me continue talking about this Calabi system that Roberto was talking about last Tuesday. So let me recall briefly the definition. So I fix X a compact complex manifold. Of dimension n. And then I fix a smooth volume form. Which I call mu. And I'm going to assume that is compatible with the orientation. So in holomorphic coordinates, this would be the canonical volume form times some positive function. And then I'm going to fix also some number. And I'm going to fix as well B0, P1 over X holomorphic vector bundles. I'm going to assume, even though it's not necessary, two things. We can work in a slightly more general setup. I will assume that the first in class of V0 is 0, as well as the one of V1. And I will also assume that the second in class of V0 equals to the second in class of V1. So the first in classes are 0, the second in classes agree. I have to say where did they agree. They agree in the 2,2 Bochern homology of X. Okay. Then for alpha bigger than 0, I say that omega h, where omega is a 1-1 form on X, which is real and positive. And H is a Hermitian metric, which I will consider to be a split. Then this pair omega h satisfies the Calabi system. With level L if the following conditions are satisfied. So one is the Hermite-Einstein equation for H with respect to omega. So here, since I have my H, which is a direct sum, what this means is that I satisfy Hermite-Einstein for both metrics. Okay. To the following condition is satisfied: e to the minus L f omega n minus 1 equals to 0, where f omega, L omega, sorry, is defined through the following equation. So if omega depends on mu, this way, and 3 TDC omega plus FH wedge FH equals to 0. Let me move this thing because it's not good. Okay. So these are the equations. So what is this sort of pairing that I'm using here? So here what I mean by FH, which FH between brackets is that is precisely minus alpha trace FH0 squared plus alpha trace FH1 squared. But I'm going to use with this, I'm going to work with this compact notation for the sake of this lecture. Okay, so all in all, we have this definition. So we have a Hermitian metric on the manifold, a pair of metrics, one of each holomorphic vector bundle, and we say that this solves the Calabi system if these three equations are satisfied. Okay. Okay, I'm going to call this CL to simplify. And then let me make some remarks that were mentioned by Roberto the other day. Remarks. So the first remark is that if I take x omega to be Calabi-Yau, and I take mu to be proportional to omega wedge omega bar, then CL is the same as the Hall-Strominger system. So for people who know what this is, may complain, because for the physics, in physics, people take B naught to be special. They take it to be, well, what they do is to take, let me denote by B naught with a double bar, the smooth bundle underlying B naught. And then in physics, people assume that B naught is a tangent 1, 0. Okay. And furthermore, many people in the math literature assume also that, or replace in math, mainly people coming from the school of Yau. So for example, if you go to the papers by Yau or Fong, etc., then instead of taking the Chern connection, which I'm going to denote by this, theta H naught, in this context of the tangent bundle, this is replaced by nabla Chern of omega. So you solve the same system, but in this equation here, in the third equation, right, you replace the Chern connection, which I'm going to take here to be a Chern connection for some abstract holomorphic structure on the bundle. People take it to be a Chern connection formula. So this in the end is an irrelevant choice. This is irrelevant if actually the tangent bundle with its holomorphic structure is polystable. This may not be the case because we are on possibly non-Kähler manifolds. But if the tangent bundle if the holomorphic tangent bundle is polystable, then this choosing one connection or the other doesn't make any difference. It just they differ by some complex case transformation. Okay, so this was my first remark. My second remark is that in this context of Halle-Strominger.
Wait, sorry, Mario, can I just interrupt?
Yeah.
I mean, I don't think I quite understand that last comment. You mean like if you can solve it with one connection, you can solve it with the other?
Yeah, that's true.
The other objects won't be the same necessarily, but just that there exists a solution. Is that what you mean?
Yeah, if you solve the Halle-Strominger equations with Nabla-Chern,
yeah,
then if the bundle is polystable with respect to the balance class, you know that there exists a unique complex gauge transformation which takes Nabla-Chern to a Hermite-Einstein connection, and this is what I would take.
I see, and you don't have.
And
to
the equations are invariant because this pairing is invariant under complex gauge transformation.
And do you have to change like the metric on the base space or anything like that, or?
Well, no, your metric on the bundle, on the tangent bundle, which was omega, now gets changed to some abstract metric. You don't know what it is.
Okay, yeah. Okay.
This is my approach, to take it abstract and make it a free parameter, because it makes life simpler and it's more geometric. But
I guess I understand you're applying like a gauge transformation to the metric on the bundle, but then there is this metric like on the base space omega. Like, what do you do to that?
Oh, in Yau's approach, my H naught will be his H associated to omega, but he has a fixed holomorphic structure, and he is not imposing the Hermite-Einstein equation for Nabla-Chern. He drops this condition.
Okay, yeah. Okay.
Yeah, I was a bit sloppy saying this. My point is that in Yau's approach, he takes this, but he drops the Hermite-Einstein equation from Nabla-Chern. So if you make that choice and the bundle is polystable and the tangent bundle is polystable, up to complex gauge transformation, you recover these other systems. You can go from one to the other.
Okay.
Up to gauge.
Okay, I think I understand. Thank you.
Okay. So for Halle-Strominger, for this special case, at least, if the rank of B naught is 0, so suppose that you have a solution of these equations, 1, 2, and 3, but now there is no H0 metric. Okay, if this is the case, then CL implies that the omega is Kähler, actually Kähler Ricci flat, and also FH1 is 0, so H1 is flat. Okay, so there is some tension between the system and the signature of this metric here. This metric cannot be positive unless we have flat. If we want solutions, then this metric cannot be positive unless if we want some non-Kähler solutions. Okay, and this somehow makes life complicated for the system. My last comment is that if both for CL, no, so no Calabi-Yau, no holomorphic volume 4, but no bundle. So if both bundles are not present, then this system of equations is the same as having a Keller metric with constant dilaton function, f omega. And this, if you recall that f omega is defined through this equation here, e to the 2f omega mu equals omega n divided by n factorial. Using this, you obtain a solution of the Calabi system, of the Calabi problem, sorry. Solution, a Keller solution. Of Calabi, of prescribing the volume. Okay, so I hope this at least motivates why we call it Calabi system. Okay, and these other remarks motivate why we are interested in these equations. At least from my point of view, I think these Halley-Strominger equations are interesting because they drop from a string theory in a nice way. Okay, so the question I want to address is existence and uniqueness. What can we say about this? Okay. So the first thing I'm going to do is talk about uniqueness. Trying to make sense of uniqueness. So uniqueness. So let me recall the equations because they are complicated and I don't assume that you have them in the top of your head. So we have FH, which is omega n minus 1 equals to 0. This is 1. Then we have this other thing, which is like a conformally balanced equation. And then we have this other thing, which is DTC omega plus FH, which FH equals to 0. I never make it to the end of the equation. I don't know why. Anyway. So if we want to address the question of uniqueness, then it is natural to fix some parameters. So it should be uniqueness up to something. Right? For uniqueness, once we have fixed some cohomological quantities. So question is then do we need, this is too big. To fix cohomological data.
Sorry, can I just ask a silly question? So this alpha thing that you are putting there in front of the traces,
yeah,
like should I think of it as another parameter of the problem, or can it be like absorbed into something else?
Yeah. You can, from your point of view, I guess you can just think of it as a choice of pairing in the Lie algebra of the structure group of the bundle of frames.
Right. Sorry.
Actually, I made. You can make it even more general by putting two constants in front of one in front of each trace, but there's no, you don't win anything with that.
Okay.
The more abstract picture will be to fix some invariant pairing in the Lie algebra of the bundle of split frames of this direct sum.
Right. Okay. Thank you.
And then you have a more general setup.
Can't you absorb it into omega?
Sorry?
Can you just absorb it into omega, though, alpha?
Yeah, but this has, you can absorb it into omega, but then maybe what I'm going to say now explains why I don't want to do that. Somehow I want to keep track of some of the cohomological quantities which are attached, and then this will change the balance class, and I will need to keep track of that. Okay, but yeah, you can absorb it. Typically, well, it depends on your point of view. So let me tell you about one point of view. So the classical point of view would be to do the following. Well, observe that because we have equation 2, we have an associated cohomology class. We can define a balance class, which is the class of e to the minus L, f omega, omega n minus 1, in the n minus 1, n minus 1 Gaussian cohomology of X. You can put an R here because it's a real cohomology class. Okay, and I call this balance class. So then one possibility to address this question is question prime is that do we have uniqueness if we fix B? Let me write where is B? B is here. Okay. We fix the balance class. And then a natural, if you want to take that path, which is very natural, I have to say, then one can do the following. One tool to address this question, Q prime, is the anomaly flow. This was invented by Fong, Picard, and Sang. It's a quite a remarkable flow, which I would like to know more about. This is the following. So on the one hand, you just have the Donaldson flow for the metric. So I hope you don't mind, but I'm going to unify the two metrics in one. It's just a product metric, okay? All the time. So this is just lambda omega t FHT, and lambda omega t denotes the contraction with the Hermitian form. And then the more interesting part of the flow is HT minus 1 partial. Oh, no, sorry. This is what I wrote. The most important part of the flow is this one. The derivative of the n minus 1 power of the balance metric that I have somehow attached to this system, which is this guy, equals, oh, here I have to do something. Let me write this, otherwise it doesn't make any sense. DDC omega plus FHT, which FHT. Okay, so this only works in n equals to 3. Okay, for 3-folds. For 3-folds, we have this interesting tool, which is called Anomaly Flow, which you see because we are assuming that the sequencing class of P naught equals to the sequencing class of P1, this term here is DDC exact. This is also DDC exact. And therefore, this preserves the balanced class. Okay. Of course, one has to do something to prove this rigorously, but essentially this is the idea. Okay, so this preserves the balanced class.
Sorry, can you just repeat what is this lambda thing in the first equation, like on the right-hand side?
Sure. Lambda is the operator which acting on a one form, on a two form is defined as follows. Lambda omega alpha is a function, and this is alpha wedge omega n minus 1 divided by n minus 1 factorial. It's just the contraction within metric.
I have a question. Doesn't the Hermitian Einstein condition that fh wedge omega raised to n minus 1 is equal to 0 imply that fh is primitive, like fht is primitive, and so the right hand side should become 0, right?
No. Here I'm not assuming.
Okay,
that,
okay.
Yeah. Let me clarify this thing.
Okay,
What is this anomaly flow approach? In the anomaly flow approach, you have these three equations, right? 1, 2, and 3.
Right, yeah.
In the anomaly flow approach, you fix a solution to 2,
okay,
and try to solve 1 and 3, preserving the balanced class. Okay, so you have a solution to 2, and then try to modify that and construct a solution of 1, 2, 3, preserving the balanced class.
Yeah, see, so at the fixed point, yeah, it becomes basically a solution.
And this is but this is the idea. Okay, so this picture, you fix here. You fix solution to 2 and try to solve for 1 and 3. Okay. Okay, and if life was simple and not as it is, then one should have a long time existence and convergence of this flow under some conditions and to a solution of the system, and they should maybe be able to to grant existence and uniqueness. We don't know that, but in any case, this is not the approach I want to take. Okay, this is certainly one possibility, and one can do that, but this is not the approach I want to. And the reason is why I don't want this approach, or one of the reasons I will need some time to explain this, maybe I can say more later, is that it seems that the balanced classes are not the right parameter. Okay. But let me try to say more in maybe 20 minutes. Okay, so this is the classical approach, right? Take this to the uniqueness question is simply fixing the balanced class and try to prove the uniqueness of solutions in the balanced class. This anomaly flow provides a tool to also attack the existence problem. Anyway, so this other approach that I'm going to talk now about is what it comes from in the work with Roberto, Carlos, and Carl. So let me go now for the stringy approach. So what is this stringy approach to this question? Well, instead of fixing the balanced class, I'm going to fix a solution of 3. So you heard from Roberto the other day, and if you thought of these Hallström equations a little bit, you realize that this third equation is kind of complicated. We don't have much control. So as we say in Spanish, if you cannot defeat them, join them, right? So since we don't know what to do with 3, let's try to embrace it as part of the geometry. So from 3, let me write knots here. So omega naught fh naught. From 3, I can construct a geometric gadget, which is a holomorphic Courant algebroid. Can construct a holomorphic Courant algebroid. Which I'm going to describe now. So what is this? This holomorphic Courant algebroid is a bit more complicated than the one that appears, for example, in my work with Joyce and Jeff. It has this other bit coming from the bundle. Okay. This is the smooth complex vector bundle underlying Q. So for simplicity again, I'm going to unify the picture, abuse of the notation, and denote this simply by NP. Okay. Has 2 pieces anyway. So now I construct a double operator, which I write in matrix form using this decomposition, these 3 pieces, tangent 1, 0, NV, tangent 1, 0 dual, as D bar, NV, D bar, and then here I have minus FH naught 2I del omega naught to FH naught, and then 0, 0, 0. Okay, so for example, you are more familiar possibly with this bit here. Did you have to think of this? This is a 2-1-4, right? So this 2-1-4, for example, I regard it as a 0-1 form with values in endomorphisms from tangent 1, 0, sorry, homomorphisms from tangent 1, 0 to tangent 1, 0 dual, right? So this 0-1 bit, the 0-1 form bit is the thing that it's a 0-1 vector field and enables you to take derivatives, okay? And this other thing, for example, minus FH naught, I regard it as a 0-1 form. So this is a 1-1 form with values in endomorphism. So I regard it as a 0-1 form with values in homomorphisms from tangent 1, 0 to NV. And the rest is similar. Okay, so here we have the tangent 1, 0 bit, the end V bit, and the tangent 1, 0. Okay. Good. I'm not going to use much of this structure. For the sake of completeness, let me mention something. So Of course, if this is a holomorphic Coulomb algebroid, there should be a pairing and a bracket. Okay. The pairing is very simple. It's similar to the usual one. So the pairing of B plus S plus alpha, my writing is getting worse and worse. B plus S plus alpha, B plus S plus alpha. This is just alpha B. So the contraction of the 1-0 form with the 1-0 vector field plus the pairing of SS. And here I use the pairing, this weird pairing that I defined before, using the traces and alpha and so on. Okay. So here S is the endomorphism bit. So essentially this is taking traces and multiplying by alpha with a difference of sign, depending on what you are. And then the bracket is somehow reminiscent of what happens in the standard situation in the smooth case. This is an alpha. This is the bracket of B prime plus del B S prime. Here I should write H naught. So this is the term connection of H naught, taking 1-0 bit and then taking derivatives. And then minus del H naught B prime S minus the endomorphism bracket of S and S prime. And then plus IV del alpha prime plus del of alpha prime V minus IV prime del alpha plus other terms. Okay, I wanted to get here because you see this is not the usual expression that I use for in the smooth case. In the smooth case, I will have something like the Lieb derivative and the zero differential. Right? Of course, this need to take values in this Q naught. Okay, my point is that this will not satisfy. This will not satisfy the usual axioms of Coulomb algebroid. Unless you take E and E prime smooth sections of this Q naught, which are furthermore holomorphic. Then you recover the usual axioms. Okay, so in order for this to satisfy the axioms, you really need to take this as a mnemotechnic rule, right? Because what it means really is that you are applying this bracket to holomorphic sections of the bundle. And then this is, you replace in the definition of Coulomb algebra, you replace smooth functions by the sheaf of holomorphic functions and everything works. Okay, let me mention something which is new in this holomorphic picture, which I think Roberto mentioned the other day. Something rather, slightly different because we have more structure. What is new in this picture? Well, what is new is that this D bar Q preserves both the structures. So the pairing is holomorphic. And also the bracket is holomorphic. Okay, so if you have two holomorphic sections and apply the bracket, then this remains hollow. And doing that, then you get the usual actions. Okay, so these two things are holomorphic.
Just to clarify, so in the expression for the bracket, when you say partial h0, that h0 is not the metric on v0, right? It's a full metric, but at some.
Oh, my notation is terrible. Yeah, because I wanted to fix a metric. Yeah, then one of the metrics is 0, 0 then, and the other one is 0, 1.
Yeah. Okay. Yeah.
Sorry. Yeah, it's the full metric. It's the full metric. I guess. Yeah. So I have fixed this. So my H naught is really H00, H01. Okay, with a plus. Yeah, sorry. I'm not going to use this unpacked notation and this is completely. Okay, good. So with this, we have associated to a solution of 3 given. So recall that given omega naught H naught such that DDC omega naught plus FH naught, which FH naught equals to 0. We associate this Q naught, which depends really, if you look at the formula, on 2I partial omega naught and the Chern connection of H0. Okay. And then, since we are asking about uniqueness, a natural thing to do is to reduce the parameters by looking at other omegas and h's, which induce isomorphic Qs. What I mean is next we're going to consider omega H satisfying 3 and such that the corresponding Q I partial omega theta H is isomorphic as a holomorphic Courant algebroid to this Q naught. Okay, so isomorphic as holomorphic Courant algebroid. Well, this is kind of technical, and I'm not going to go into that. I'm just going to give you the definition. So, what are the omegas and h's which satisfy 3 and fulfill this condition? And this is my next definition. So, definition. This is one of the things that Roberto was talking about the other day. Seen from a more pedestrian way. A compact form on Q naught. Recall that this is the Q associated to 2I partial omega naught and the Chern connection of each naught is given by 3 things: omega plus beta H, where omega plus beta is, well, has 2 bits. The omega is a real 1-1 form on X. No positivity condition imposed. Just any real 1-1 form. And beta is a 2-0 form on X. And then H is a metric on B, which I'm implicitly assuming that is a split and each bit lives in one of the 2 bundles, okay? And these are just the parameters, but of course, I want to impose that this satisfies 3 in a sense, and furthermore, the corresponding holomorphic Courant algebroid is isomorphic to Q0, and I do it all at once with the following equation, such that d beta equals 2i partial omega minus 2i partial omega naught minus 2a wedge fh, where a equals the difference of the Chern connections of H and H naught. It's the other way around. This is theta H minus theta H naught. Therefore, this is a 1-0 form with values in endomorphisms of B. Okay, there are more terms. Sorry about that. Minus a wedge d H naught a minus 1/3 a wedge a. Okay. So my claim now, at least this makes sense as a formula, right? This is a formula for 3-0 plus 2-1 forms. And my claim is that DDC omega plus FH, which FH equals to 0. Okay. But this condition is stronger. Okay. So how do you prove that? Well, you need to realize the proof is to realize that this mesh on the right-hand side let me call this triangle. The proof is that triangle equals something more geometric, which is the Chern-Simons tree form associated to H minus the Chern-Simons tree form associated to H naught minus T of theta H naught, theta H, and I think I'm messing up with the knots. It's the other way. And if you do this, if you realize this and use the formula for the differential, if you want the canonical property of the Chern-Simons tree form, D of the Chern-Simons tree form is precisely FH, which FH, and then you get the formula. Okay. So notice that this makes perfect sense on the manifold, but the Chern-Simons tree forms live on the total space of the bundle of frames, blah, 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 blah. Okay. But this is the way you prove it in an economic way. Otherwise, you need to take differentials. Okay. Okay, so far so good. Then let me give you an abstract definition just for the sake of completeness and to link with what Roberto was saying the other day. Definition. The other day, Roberto was introducing some names. One was a string, Courant algebra. The other one was Botchern, Courant algebra. So let me give you a definition which motivates it. So definition, let Q be some abstract holomorphic Courant algebroid. And we say that Q is Botchern type if Q is isomorphic to Q2I partial omega naught theta H naught for some omega naught H naught solving 3. Okay, this is one of these abstract definitions that Roberto was saying. So can now deal with more general abstract holomorphic Courant algebroids if you want, and then see that these are going to be of Botchern type if they are of this specific, if they are isomorphic to one of these specific form. And in more.
Can I ask a question about?
Sure.
Is it if Q is if you know it's already a holomorphic Courant algebroid and it is isomorphic and you can write it down like the way above, doesn't that it doesn't imply that equation 3 is solved?
Yeah.
Like so the thing that you wrote solving 3 is kind of it doesn't need to be there, it's automatic.
Well, otherwise this is not a holomorphic Courant algebra. So I couldn't talk about an isomorphism.
I see. Okay, I see what you mean.
In more abstract terms, this Botchern is the same. This is just an aside comment. It's the same as the existence of a compact form in the following more geometric sense. If you take the holomorphic Courant algebroid Q, add these two bits, then Roberto was explaining the other day that there is a canonical way of constructing a bracket, a pairing, and so on this guy on the right-hand side, making it a smooth, complex Courant algebra. If this admits a compact form, meaning that if it admits an embedded real Courant algebra, then this is Botchern, it's equivalent. Okay, this is a more geometric way of saying this. But then I'm going to work with this very explicit definition here instead. Okay, this thing. It's a bit nasty, but at least we can, it's just something that has to do with differential forms. Okay, good. So then we can then ask how many parameters do we fix with this? We are asking about uniqueness for the Carabi system. And then we can ask if we fix this Bochern algebroid, this holomorphic algebroid of a spatial type, and we consider only omegas and h's solving 3, which live in the same guy, then how many parameters I fixed from omega and h? Okay, and this is the content of the next proposition. Proposition: the set of isomorphism classes of Bochern algebroids with fixed B so with fixed holomorphic vector bundle, and this is the problem I'm interested in really, are in correspondence with Im of a suitable map. I'm going to call partial, where partial is the canonical map that goes from the 1-1 real applic homology of the manifold to the first check homology of the sheaf of closed to zero forms, in particular holomorphic, modulo something. And this sigma B is an homomorphism from the group of automorphisms of the holomorphic vector bundle into this guy, which is canonical. So if you want, if there are no automorphisms, if your bundle is simple, then you can forget about this part, and then you just have this first check homology, which classifies exact holomorphic kernel algebras. Okay, so what is this map? This map here, partial of the class of alpha, where alpha is DTC closed, is simply the class of partial alpha. And if you forget about this Im sigma B, then there is no. Okay. The last bracket is just redundant. So recall here, in case it's not on the top of your head, that H1 omega to 0 close. This can be described by a result by Marco Gualtieri as the curl of D going from 3, 0 plus 2, 1 to the next guy, modulo the Im of D from 2, 0 to 3, 0 plus 2, 1. Okay. So this is what I use here really for the definition of this map. Okay. So if I take alpha, which is DTC close, I take del. And now this is a 3, 0 plus 2, 1 form, which is D closed. And I take its class, modulo the image of D. Okay. Going from 2, 0, 4. Okay. Good. So what this gives us a glimpse on how many parameters we are fixing, right? Also, this gives us some information about the structure of this Bochern algebroid. This Bochern algebroid, so you can make it more general for holomorphic algebra. In essentially, this sort of transitive holomorphic kernel algebroids are somehow the classifying space for them. The set of isomorphism classes is a torsor for the set of isomorphism classes of exact holomorphic kernel algebroids, which is this guy. So essentially, if I fix one of these guys, then the others differ by shifting by an exact guy. Essentially. what this suggests, besides the fact that it gives us information about what we are fixing with this, what this suggests is that the 1-1 applic homology should play a role in this story, right? Something is going on with the 1-1 applic homology here. And this hopefully motivates my next definition. So observe that there are further degrees of freedom for solutions of 3, for solutions of 3 coming from the kernel of this map. Inside the 1-1 applic homology of 1-9. Okay, so this, I'm not sure if everyone remembers this. This is Kerr of del bar modulo in del plus del bar with the right degrees. Okay.
Can I ask a question?
Sure. Yes.
When you're considering isomorphism classes of the Bot-Chern current algebroids with a fixed V, are you identifying them if they're related by that kind of beta thing that you were?
Yeah.
They're and so does that thing related to the kernel of delta then?
I mean, there is you can write it explicitly. I'm cheating a bit because I'm making the morphisms more restrictive than the ones of holomorphic current antibody. And this is why we call these things a string something. So there is some further conditions that you can put on your holomorphic current algebroid to make the morphisms more restrictive, just given by exact morphisms. And
So
we are classifying up to that.
You're classifying up to this thing of adding the beta.
Yeah, but essentially the classification stands for this. Oops, is this formula? So the conditions that you need to impose are this formula here. But there is some other piece of data, which is a gauge transformation. So it's not only this formula, but you can also modify your theta h in the formula by a complex gauge transformation.
Is that what you're modding out by?
Yeah.
And is the kernel of delta related to this choice of beta? Or no, I guess it can't be.
No, the kernel of no. This only sees the omega part. But the fact that the beta exists places your class of omega. This is not well defined. I'm going to define it now. It places it in a very particular part of the 1-1 applic homology. So it has to do with where it lives. But it's not using omega. It doesn't see omega at all because the way you construct these applic classes is just by taking D in this equation. It doesn't use omega. Beta, sorry, it doesn't use beta too.
It only sees omega.
Yeah.
But the beta is coming in to change omega.
Yeah, the beta is, you can think of it as an isomorphism of as part of an isomorphism of holomorphic current algebroids. Yeah. Okay. So this motivates the following definition. I'm going to denote by BQ not the space of compact forms on Q naught. Recall that we have this complicated definition, but an element in here, in the end, is a pair omega h, which satisfies 3. And this is all you need to know at this point. And now I'm going to say that two elements here, omega 2, h2, and omega 1, h1, are related if and only if omega 2 minus omega 1 minus the Bochern secondary characteristics class associated to h2 and h1, I explain now what this is, belongs to im of del plus del bar. So what is this gadget here? This is an interesting thing. This is a R is a Bochern secondary class. It has some axiomatic definitions, but let me give you two essential properties. No, three essential properties. So the first comment is that where this lives. So R of H2, H1 for any pair of metrics lives in 1-1 forms on X, actually real, modulo im del plus del bar. So it's not a well-defined 1-1 form. It's only well-defined up to shifting by del plus del bar. This R satisfies a Cosyco condition. In this space where it lives. I think I wrote this properly. I always need to check where to put the sign. It's correct. Yes, it's correct. Then the other thing we need to know about this thing is that DDC of R H2 H1, of course, R F2 H1 is only defined up to del plus del bar term, and therefore DDC of it is well defined. And this is precisely F H2 with which FH2 minus FH1 which FH1 and 3 is just that it can be calculated explicitly, and this is due to Donaldson. 3 is an observation by Donaldson. The other bits are appearing works by Bismuth, Gillier, and Soule. So this is Donaldson. This is Bismuth. Et al. is that I can calculate R is to H1 as minus I times the integral from 0 to 1 of HT minus 1 HT dot F HT dt for some curve. Joining H2 and H1. Okay. So what is the idea behind this proposition or this definition? Sorry. If you have two solutions of this Bianchi identity of equation 3, there is no Apli class associated to them. But if you subtract the two solutions, then there is an Apli class. Okay. And what this equivalence is saying is that when you subtract, you get something which is in the same Apli class. Okay. So just an aside comment. An aside comment is that if I have two compact forms, omega 2 is to omega 1 H1 in BQ naught, both satisfy equation 3, and therefore DDC omega 2 minus omega 1 equals FH1 wedge FH1 minus FH2 wedge H2. And now I apply condition 2, and this is BDC of R of H1 H2. And this is minus DDC of R H2 H1 by the Coseco condition. Okay. So this means that omega 2 minus omega 1 plus R H2 H1 has a well-defined Apli class. And what this definition is saying is that two things are related if the Apli class is the same. Sorry, if the Apli class is 0. Okay. Two things are related. So whenever I have two solutions of equation 3, I can associate an Apli class via this Bochern secondary class. And two things are related if this Apli class is 0. Okay. I think I wrote this in the wrong. There is some sign which is wrong. This plus here, maybe some minus. Here I wrote a minus, maybe it's a plus. I think it's a plus. Yeah, it doesn't matter. Okay. So this is the idea. And now I was trying to define something. So okay, I define this thing. Essentially, the Coseco condition. So 1 is condition 1 here. Implies that this is an equivalence relation. So there is a well-defined equivalence relation defined in the space of compact forms of Q. So condition 1, what's this thing? Yeah, 1 implies that this is an equivalence relation. And then I can define. So Q not bot churn. Then the set of apply classes of Q not is, by definition, I call this sigma Q not, and this is B Q not modulo this equivalence. And I want to interpret this as a cohomology group. Okay. Essentially, it's the same sort of thing that you do when you construct cohomology. You mod out by the exact things. And the point is that here things are more complicated because you need to take from the hat this bot churn secondary class. Okay. So now with this.
Can I ask a question?
Sure, yeah.
I'm just a little bit confused about this BQ not. Why, like, it doesn't seem to be actually associated to Q naught. It seems like it's just all bot churn current algebroids with the same vector bundle V. Or am I wrong?
I don't know. So BQ naught is a space of compact forms on Q naught. The space of compact forms.
When you had compact forms, they had to satisfy an extra equation, not just equation.
Yeah.
Oh,
This complicated equation before. So these are omega plus beta and h's, such that d of beta equals 2i partial omega minus 2i partial omega naught, and then a mess. But if you want to think of it in more abstract terms, these are omega. No, I cannot do that. Yeah, no, this is all I can. Yeah.
So it's a set of bot churn algebroids that are isomorphic to Q naught.
No, it's not. It's not. These are compact forms. These are what this is parameterizing. If you want to think invariantly, what this is parameterizing are real current algebroids inside Q naught plus tangent 0, 1 plus tangent 0, 1 dual. This is what this is parameterizing. Q naught is fixed, and you're parameterizing these gadgets. And this is an inclusion, and this needs to be compatible with the pairing. So it is an involutive subbundle of this guy. But it's not the isomorphism class of Qs. Are these real guys? And another way of thinking, if you fix one, another way of thinking is that you have, if you call this EQ naught, then BQ naught, this is not obvious, but it's true, is out of EQ naught modulo out of ER for some fixed compact form. So this is really like the symmetric space associated to, it's like the space of metrics. Okay. It's not isomorphism classes of watching. Okay, so I'm saying all this because now I have identified what is in the kernel of the partial map. So proposition or lemma, whatever. Sigma Q naught is an affine space. Which is modeled on the kernel of partial, where partial is as before, the map going from 1,1 apli homology to H1 omega to 0 closed. Okay, and let me ignore the automorphism. So say, of course, one needs to, so say that automorphisms of the are trivial. Otherwise, you need to quotient by some further thing. Okay. So what we have done with this construction, so the upshot of this construction is that we have decomposed the 1,1 apli homology of the manifold in a interesting way. We have decomposed it as Kerr partial plus impartial. And I want to think of this as holomorphic parameters because they classify both Chern algebroids. And I want to think of this as scalar parameters or metric parameters. Okay. So if this, okay, so there is something maybe that I can comment now on respect to the classical approach, right? Recalling the classical approach, there's a comment relation to classical approach. Well, recall that there is an isomorphism between the dual of this and the n-1, a-1 with Chern homology. And now, interestingly, we have two things. On the one hand, we have the balance class of the solution. If we have a solution, we have the balance class living in here. And if I have fixed a Q, I can associate an apli class. Which is the class of my omega and H in this abstract space sigma Q naught. But if I have fixed one particular omega naught and H naught to solve this Bianchi identity, this DTC omega, then I can regard this actually as a class in 1-1 cohomology, an ordinary class, no mystery. And because of things I'm doing with Arpan here in the audience with Arpan Saha, there seems to be a very interesting relationship between these two things, these ably and balanced classes. And it's not at all obvious. But morally, if we think of these impartial as holomorphic parameters, then it may happen, it could happen, that for suitable Qs, I may not be able to solve the equation, but just for others. So what this means is that morally, the set of Bs, the set of balanced classes, is going to be constrained. Okay? And this is why I think that this classical approach just doesn't work. Okay? And you need to take this stringy, funky approach to make sense of this. And to finish, yeah, I was expecting to go much further, but yes, to finish, let me give you an interpretation of this Calabi system with all this machinery in place using some functional. So now what comes is this dilaton, the dilaton functional, which is the tool in the classical picture. In 3 lines, I was able to tell you what I was fixing and what was the tool to attack the problem. And here I needed a bit more of space. So the dilaton functional is the tool Do you hear me? Okay, wait, yes, my computer died, but I'm still here. No.
Yeah, no, we hear you fine.
I forgot to plug in the computer. So where is this thing? Then it's a tool to address the existence question and uniqueness question in the stringy approach. Okay, so what is this thing? It's, in a few words, we fix Q naught, which I can regard it as the Q of some solution of equation 3. So I fix one solution of equation 3. I consider the space of compact forms. Take the Q naught space of compact forms. And then define the following definition: M L of omega h for omega h a compact form in Q0. So recall that being a compact form in Q0 means that it satisfies this complicated differential equation, which is some integration of the Bianchi identity. So it's a current equation for 3 forms instead of 4 forms. This is equal to the integral of over x. And I need to remind myself about the normalization because I always forget about this thing. The integral over x of e to the minus L omega n divided by n factorial. Recall that e to the 2 f omega mu is the volume. This is a functional, which we call dilaton functional, because it has to do with something called the 4-dimensional dilaton, or the dilaton of the 4-dimensional effective field theory in aderitic string compactification. And then the proposition is the following. Critical points of ML along a fixed Apli class let me denote it by this. Recall this is a fine model on the kernel of partial. Are solutions to the Calabi system. And what do I mean by this? Because now the magic here, or the thing we are doing, is that any omega h in BQ0 already satisfies 3. So I only take care about the first 2 equations of the system. So what I mean is that this satisfies FH, which omega n minus 1 equals to 0, and then this was 1, and then d of e to the minus L f omega n minus 1 equals to 0.
Sorry, Mario, can you remind me, what is the parameter L again? I forgot the parameter L.
The main consequence of this construction. And the proof is very simple. You just take variations brutally of ML, forgetting about that you are in holomorphic current algebras or anything. Right? Let me do the proof. The proof is very simple. So if we take variation of ML, what do we get? We get integral over x. Let me call this is the variation of ML. So let me call alpha to the variation of omega and s to h minus 1 variation of h. Then, because the function only depends on omega, I can forget about the h. Then this is just minus L variation of f omega alpha e to the minus L f omega n divided by n factorial plus integral over x of e to the minus L f omega lambda omega alpha omega n divided by n factorial. And now, because of the definition of f omega, e to the 2f omega mu is omega to the n divided by n factorial, then the variation of f omega along alpha is 1/2 of lambda omega alpha. Right, and then arranging the terms, you get something like 1 minus L over 2
Hey, Mario.
over x e to the minus L f omega L alpha wedge omega n minus 1 divided by n minus 1 factorial. Okay, and this is just the variation of omega. This is I don't need current algebras or anything here. This is just I vary this functional with respect to the metric, no? And now I apply the fact that this has to do with a current algebra. If omega h is varying along an elliptic class, it means that alpha minus the variation of this R H H naught is going to be del of something plus d bar of something. But now the variation of H naught is minus up to sign or something which I never remember. S, recall that S is the variation of delta times H minus 1. So this is, well, I write it explicitly because otherwise it makes sense. This is H minus 1 delta H. This is by this formula by Donaldson times the curvature of FH. And this is del of G plus d bar of G bar. And now you are done. If you are in a critical point, this is 0. But now you substitute alpha. And the fact that you have the freedom of the G's and the delta H's gives you two conditions. The G's give you the condition that gives you the conformally balanced condition, and varying the metric gives you the Hermite-Einstein equation. Okay. You just substitute this thing in there, apply that you have a critical point, and use that the parameters G's and delta H's here are independent. Okay, so this gives you the proof. So you see this functional is nice only if you restrict the parameters. Okay, it's only nice along elliptic classes. Otherwise, it does nothing. There is no this quantity is only good along AP classes. Are you, Jeff, are you trying to ask a question? Or I see your hand is raised.
Can you hear me now? Oh. Well, yeah, no. Anyways, maybe let's thank Mario quickly for the very nice talk, and we can ask some more questions. Yeah.
My expectation is that in this moment map construction, there should be some sort of determinant line bundle.
Mm-hmm.
So there should be a pre-quantization of the symplectic structure, which gives you this Calabi system as a moment map.
Oh,
and this L is a power of the line bundle. This L is a number that you use to raise the line bundle to some power of it.
I see.
But this is a very delicate parameter.
Right. Yeah.
And we introduced this parameter in this other paper about gauge theory for string algebroids because we realized that if you now change your perspective and think of this dilaton functional as a Keller potential, the positivity is very sensitive to the parameter. And for some values of the parameter, the metric becomes more positive.
I see. Okay, yeah.
So this was our motivation for introducing this parameter, that we realized that maybe for some for suitable values of the parameter, one can actually prove uniqueness or some obstructions because the metric on the space of parameters is more positive. I'm not saying that it's positive. I'm saying just that it is more positive because precisely because of this weird definition of this pairing. So recall that we have this pairing on endomorphism, which is like alpha trace minus alpha trace plus alpha trace.
Mm-hmm.
The metric always has negative directions coming from here.
Right.
I mean, the metric in the space of parameters, like the modular space metric.
Right.
Anyway, so this was the motivation that. So I think that there should be some construction, some sort of pre-quantization of the moment map picture that we have, where the parameter L has the meaning of raising the line bundle to some power.
I see, that's interesting. Are there other questions? I guess I sort of wondered if you could just repeat this kind of thing you said at the end with this like construction of script A. You were kind of saying that it sounded like you were saying it was sort of like an abstraction that the stringy approach like naturally takes into account or something like this. I didn't really understand, I think.
Yeah.
Yeah,
so,
like the relation to the classical picture. You made some comment here, like.
Yeah, my comment is that it is not clear to me how to detect which balance classes are achieved by solutions.
Okay.
And I see no reason why all balance classes are actually balance classes of solutions. And if I think in terms of, because we have this moment map picture and so on, these parameters in the image of partial, which I think of holomorphic parameters, may be obstructed.
I see. Okay, I think.
Because there may be some stability condition which tells you that for suitable element in impartial, you cannot solve the equations. If this is the case, then morally, some of the balance, at least some directions in the balance cone are going to be obstructed.
Right. Okay.
So this is why this classical approach loses too much information. It seems to be, I mean, maybe in the end, the answer is that it is correct, and you can also think of classically in terms of balanced classes, but from this picture, I seriously doubt it now. Yeah.
I see. That's interesting.
Yeah. For example, you may find, because we don't know anything about how AP classes go to balanced classes in this picture for solutions, I mean. So you may find a situation where in the same balanced class, you shall have two solutions, for example. So there may be no uniqueness in the balanced class,
I see.
because the actual Keller parameter is the AP class.
Oh, I see. Yeah.
Yeah, I mean, I don't know. With some of the things I'm doing with ARPAN, seems to suggest that this is actually not the case, that the map from Maple to balanced seems to be pretty good. But I don't know.
That makes sense. Other questions?
I'm sorry, because my laptop died. I had the sound in my laptop, and then I didn't realize that I was.
Oh yeah. No, it's okay. It's okay. It was only like for a few minutes.
But you could hear me.
Yeah, yeah.
But I couldn't hear you.
Well, okay. Let's thank Mario again for the nice talk. So yeah. Thanks.
Thank you.